Hello students, I am Sachitrakar. Welcome to Cars Physics. This is my lecture 3 on the subject electric charge and electric field, which comes under the units electrostatics. Okay. In previous lectures, we have discussed about definition or what's a charge, what are different properties of charge, and what are the methods of charging or electrification. Okay. Now, we will discuss about electrostatic force, means force between two charges at rest. Okay. To have idea about electrostatic force, we have to go through Coulomb's law. Okay. Then, in today's lecture, means in lecture 3, we will study about these 3 points: point charge, then we will move to Coulomb's law, then relative permittivity, of course, it comes under Coulomb's law. Okay. So basically we will study about point charge and Coulomb's law. In lecture 4, we will completely analyze Coulomb's law. Okay. In lecture 4, we will discuss Coulomb's law in vector form. Coulomb's law gives idea about electrostatic force between two point charges at rest. Okay. So, Coulomb's law in vector form, since force is a vector quantity. Okay. Then validity of Coulomb's law. Then comparison between electrostatic force and gravitational force. And finally, we will have idea on superposition effect of electrostatic forces. Then, completing lecture 4, we will attempt numericals on the basis of Coulomb's law and superposition effect of electrostatic forces. Okay. Then let's start our lecture 3 from point charge. Okay. I am erasing all these things. Point charge. What is meant by point charge? See students, first we have to understand what's a point. What's a point? This is a point. What do you understand from this a point? Point has no length, no area and no volume. Means directly speaking, our assumption is point has no dimensions. Okay. Such a vanishingly small point is, we don't consider its dimensions. Okay. So there are different understandings behind point charge. Okay. In simple way, we can say point charge is the charge which located at a point. Okay. But how can you compare point charge? Means point. Okay. Coulomb's law gives an idea about electrostatic force between two point charges. Okay. Let's consider this is a point and this is a point. There are two charges Q1 and Q2. Again, when we say about charge, the first thing comes in our mind that charge, electron or proton. Okay. Then point charge. As we know, charge always associated with mass. Charge always comes with mass. So, where there is charge, there must be mass. Okay. So, point charge means it's such a small particle on which charge resides. If the size of the particle is extremely small or vanishingly small on which the charge resides, then it may be called as a point charge. Again, you will know, if a body or if a particle losses or gains electron, then the particle or the body is said to be charged. Okay. Thus, the size of the particle is so small on which the charge resides is called as point charge. Again, another consideration means comparison. Suppose we do consider Q1 and Q2 are 2 point charges. Then comparison this point of this point. This point is so small, means this point must be very small as compared to the distance between the two charges. If distance between Q1 and Q2, which is R, is much larger as compared to this point, okay, then this is called as point charge. Of course, we have different angles to discuss point charge. What we usually discuss if charge is given to a body. Obviously, I am considering or discussing about conducting body. If charge is given to a conducting body, as we know, no charge remains inside the body. Okay, due to mutual repulsion between the charges are distributed on the surface of the conducting charged body. Okay, let's consider a small spherical conducting body. Okay, this is center of the sphere. Okay, this is a point which is center. Okay. What do we consider from very beginning? Spherical charged body. Number one, sphere is such a geometrical figure, or sphere is such a body. Of any point on the surface of sphere are equidistant from the center. Any point on the surface of sphere at a distance r from the center of the sphere. So spherical body is considered as a perfectly smooth body, since all the points on the surface of sphere are equidistant from the center of the sphere. So we do here consider a small spherical body. Suppose this body is given some charge. Either the body loses electron or gains electron. Suppose this body has gained some electron, then obviously the body becomes negatively charged. And as we have discussed, charge given to a body doesn't reside inside the body, but the total charge is distributed on the surface, because due to mutual force of repulsion between the similar charges, the charges are distributed on the surface so as to neutralize the mutual force of repulsion between them. The charges are distributed on the surface of sphere. Suppose the spherical body or a conducting body has negative charge. Total negative charge is distributed on the surface, means charge is distributed on the surface, but the charge or the charges do not move outside of the sphere, because outside of the sphere is air, and as we have discussed, air is an insulating medium and charge always seeks a conducting path to move. Okay, so whole charge given to a body, conducting body, resides on the surface of the body. Okay, if we consider a small spherical body which is negatively charged, total negative charge is distributed on the surface of sphere uniformly. Okay, that's why we have considered spherical body. The surface is perfectly smooth, so distribution of charge may be assumed to be perfectly uniform on the surface of a spherical body. Okay, if charge is distributed on the surface uniformly, then we may consider total charge of this body is assumed to be concentrated at the center of the body. Let total charge is minus q, which is assumed to be concentrated at the center of the body, or here at the center of the sphere. See students, point charge is more similar discussion as that of center of mass or point mass. As we have discussed, as you know, practically whole mass of the body is distributed throughout it. Mass of this marker pen is distributed throughout the body, but conventionally we assume that total mass of the body is concentrated at a point. That point is point mass, or that point is called as center of mass. In similar way, actual charge is distributed on the surface of conducting body, and whole charge is assumed to be concentrated at the at a point. That point is point charge. Okay. So for a spherical body, the position of point charge is at geometric center of the sphere. So in usual form, in general form, we may assume, these are all assumptions, students. If charge is given to a regular body, then position of point charge means concentration of total charge given to the body may be assumed to be concentrated at the center, means geometric center of the body. Thus, if charge is given to a regular body, then total charge is assumed to be concentrated at the center of the body, means at the geometric center of the body, which may be treated as a point charge. Okay. If charge is given to an irregular body, suppose this is a body of any shape, irregular body but conducting body. Suppose this body is positively charged, because they means this body has lost some electrons. So body is positively charged, so we may assume total positive charge is distributed on the surface, but here it may be noted that if surface is irregular, then distribution of charge will not be uniform, means on the surface distribution of charge will be non-uniform. We'll discuss it in a later stage, how charge density depends upon distance. Okay. So charge is distributed on the surface and total charge is assumed to be concentrated plus Q positive charge at a point. This is point charge. Then for an irregular body, position of point charge may be considered to be at center of mass of the irregular body. Thus, in general assumption, we may say for a regular body, position of concentration of total charge or position of point charge may be taken as the geometric center of the body. For an irregular body, position of point charge or concentration of total charge may be assumed to be at center of mass of the body. Okay. So these are different angles to discuss on point charge, but here we may simply say the size of the point is so small as compared to distance between two charges. Okay. This is about point charge. Then Coulomb's law. Coulomb's law. See, students, the observation or the experiment of Coulomb's law is much similar to the observation or experiment of Newton's law of gravitation. Okay, you will know it in this class. Okay, suppose we have taken 2 point charges Q1 and Q2, like distance between them is R. So what were the experiments, different types of observations? Okay, keeping the distance between two charges constant, means if R means distance between two charges is kept constant. As we know, you know it previously, between similar charges there will be repulsion, positive or negative, there will be repulsion. Between dissimilar charges, means between positive and negative, there will be force of attraction. Okay. If distance between two charges or 2 point charges is kept constant, then on different experiments the forces were measured, varying means changing the values of magnitudes of Q1 and Q2. Let in first case Q1 is equal to Q2, magnitude of charge is taken to be let 2 Coulomb. Okay, R is constant. Okay, let now force is calculated F1. Now the magnitude of charges are increased, means let the magnitude of charges is now doubled. Then in second case Q1 is equal to Q2 is equal to 4 Coulomb. Okay, so by doubling the magnitude of charge, it is found that the magnitude of force between them becomes quadrupled or 4 times. Okay. From this observation, it is found that the magnitude of force of attraction or repulsion between 2-point charges varies directly as the product of magnitude of charges. In first case, let force is F1 proportional to product of Q1 and Q2. In this case, in second case, let Q1 becomes Q1 dash, Q2 becomes Q2 dash, and each one of magnitude is 4 Coulomb. In second case, F2 magnitude of force becomes proportional to Q1 dash and Q2 dash. Okay. If you now compare between them, F2 divided by F1, then it will be Q1 dash, Q2 dash divided by Q1 into Q2. So F2 by F1 is equal to Q1 dash 4 Coulomb, Q2 dash 4 Coulomb, Q1 2 Coulomb, Q2 2 Coulomb. Then F2 by F1 becomes 4. Means F2 becomes 4 times of F1. Similarly, it is also observed that if magnitude of charge is halved, then magnitude of force decreases. So, this type of experiments or observations concluded that magnitude of force of attraction or repulsion, positive, positive, negative, negative, or maybe positive, negative. Magnitude of force of attraction or repulsion varies directly as the product of magnitude of charges. Okay. Then, next observation. This relation comes when distance between the charges is kept constant. Okay. Now, keeping the value of Q1 and Q2, the magnitude of Q1 and Q2 are kept constant. Okay. Then, it is observed that if distance between the two charges is decreased, then force between them increases and vice versa. Means if distance between 2-point charges is decreased, then force between them increases, and distance between two charges, if increased, force decreases, and if distance is decreased, then force increases. Okay. Again, if distance between two charges increased, then this was observation, then force between them decreased. Okay. If distance between two charges is decreased, then magnitude of force between the charges increased. Okay. Then how much the increase or decrease in force, how much? Let initially distance is R1, which is 2 meter, as that of in case of magnitude of charges were double. Now we are increasing the distance between the two charges, finally becomes R2, let it becomes 4 meter. Then in case of distance R1, force is F1, and when distance becomes R2, force becomes F2. Okay. If distance is doubled, 2 meter to 4 meter, then it is found that force becomes 1/4. How? Force becomes 1/4 if distance is doubled. Then we can relate now force, that force is inversely proportional to square of distance between the charges. Means in first case, F1 is proportional to R1 square. In second case, F2 is inversely proportional to R2 square. And obviously, if we take ratio of F2 to F1, then it will come R2 square. R1 square divided by R2 square. And if R1 is 2 meter, R2 is 4 meter, then this is 2 by 4 square, means F2 by F1 is equal to 2 square 4, 4 square 16, means 1 by 4. Okay. Thus, F2 becomes 1/4 of F1. Okay. If distance is doubled, then force becomes 1/4. So, this observation shows that force is inversely proportional to square of distance, and from first observation, if distance is kept constant, then force is directly proportional to product of magnitude of charges. These were observations. Okay. This is force inversely proportional to square of distance. Force inversely proportional to square of distance. This is called as inverse square law. Okay. Of course, in Newton's law of gravitation, you know the gravitational force of attraction between two bodies G m1 m2 by r square. So here also force inversely proportional to square of distance means we may say both electrostatic force and gravitational force obey inverse square law. Okay. Then now we'll move to Coulomb's law. Okay. We have already discussed on the basis of experiment. Okay. According to Coulomb's law, the force means magnitude of force. Coulomb's law gives idea about magnitude of force, and later on we'll decide the direction of force, how the direction is determined, attraction or repulsion. The magnitude of force of attraction or repulsion between two point charges varies directly as the product of magnitude of the charges and inversely as the square of distance between them. Okay. Let's consider 2-point charges Q1 and this point charge is Q2. Distance between them is R. Then as we have discussed, according to Coulomb's law, the magnitude of force of attraction or repulsion, whatever may be. Okay. The magnitude of force of attraction or repulsion between 2-point charges, let F, varies directly as the product of magnitude of charges and varies inversely as the square of distance between them. This is in accordance with Coulomb's law of electrostatics. Okay. Now I can erase this. Very simple definition of Wien's law. You can remember at once just by after understanding. Okay. Coulomb's law. So here force is directly proportional to magnitude of force, directly proportional to product of magnitude of charges, and inversely proportional to square of distance. We can write force is proportional to Q1 Q2 by R square. So F is equal to a constant into Q1 Q2 by R square. Okay. Where K is, I am representing here Q1, this is Q2, this is R. Okay. Where K is constant of proportionality, okay, which depends upon the nature of medium between the charges. Okay, which depends upon nature of medium. This much is enough. Okay, where K is constant of proportionality, which depends upon the nature of medium, means in which medium the charges are be placed. K depends upon nature of medium. Okay. Then now, first we will get what is K. K is constant in MKS, or we may consider in SI. K. K is equal to 1 divided by 4 pi epsilon. But before that, what is the expression of K? Means constant of proportionality. Force into square of distance divided by the product of charges. Okay. In MKS or SI, the units of constant of proportionality. Force is Newton, square of distance, meter square, and Q1 into Q2 means charge into charge, and as we know, charge is a derived quantity in SI, and units of charge is Coulomb, and dimensions of charge are ampere, means A to the power 1 into T to the power 1. So, Coulomb into Coulomb, Coulomb square. So, we may take Newton meter square per Coulomb square. We will use ampere means in dimensional formula. Then dimensional formula of constant of proportionality. Newton means force, dimensional formula of force. Meter square means L to the power 2. Coulomb square, ampere into second, A to the power 2, T to the power 2. Coulomb square, ampere square, second square means dimensional formula, A to the power 2, T to the power 2. Now we can solve it to get dimensional formula of K, M to the power 1, L to the power 3, T to the power minus 4, and A to the power minus 2. Okay. Then K is equal to 1 by 4 pi epsilon. K depends upon nature of medium, but 1 by 4 pi is constant. Then how K depends upon nature of medium? Then about this epsilon. Okay. What is epsilon? Epsilon is called as permittivity. Okay. Which depends upon nature of medium. Epsilon is permittivity, which depends upon nature of medium, for which, since epsilon depends upon nature of medium, so K depends upon nature of medium. Okay. Then, what's epsilon? Epsilon is equal to epsilon naught into epsilon r. Okay. Epsilon naught is called as permittivity of free space. What is free space? Free space means vacuum, where there is nothing, that is free space. Of course, we do consider epsilon naught in air also. So usually the proper form is epsilon 0 is permittivity of free space or vacuum. We may consider in air medium. Okay, but it's some extent different. We do consider so. So permittivity of free space means vacuum. The magnitude of epsilon naught is constant. We have to remember it. 8.85 into 10 to the power minus 12. Units is just reciprocal of units of constant of proportionality. Coulomb square divided by Newton meter square. Okay. This is about epsilon naught. Permittivity of free space. Okay. K. K is 1 by 4 pi epsilon naught, and units we have written Newton meter square divided by Coulomb square. Okay. Then epsilon is equal to epsilon naught, epsilon naught. K is equal to 1 divided by 4 pi epsilon. So K is equal to 1 divided by 4 pi epsilon naught into epsilon r in place of epsilon. Okay. Then now epsilon r, which is called as relative permittivity, or epsilon r is also called as dielectric constant. Dielectric constant. I think we have discussed a little bit about dielectric. Okay. Dielectric determines the nature of insulator. Okay, insulating property. Dielectric determines insulating property, and epsilon r is called as dielectric constant, or other name is specific inductive capacity, SIC. Okay. So now our discussion is relative permittivity. See students, K is a constant which depends upon nature of medium. Finally, K is equal to 1 divided by 4 pi into epsilon 0 into epsilon r. Okay. Here the value of 4 pi epsilon naught is constant, since epsilon naught value is given, and 4 pi 1 by 4 pi is constant. Again epsilon 0, value of or magnitude of epsilon naught is constant, means 1 by 4 pi epsilon 0 is constant. Then how K depends upon nature of medium? Because epsilon r means relative permittivity depends upon nature of medium. So since epsilon r means relative permittivity depends upon nature of medium, so K depends upon nature of medium. Why K? Constant of proportionality depends upon medium, because K is related to relative permittivity as K is equal to 1 divided by 4 pi epsilon naught into epsilon r. So since relative permittivity or epsilon r depends upon nature of medium, so K, constant of proportionality, depends upon nature of medium. Okay. And I think you have taken the screenshot. Okay. You have to remember some values of epsilon r, and if you are approaching numericals, the value of epsilon r you don't know, then it must be given in your question. But the general values for vacuum, or you may take for air, for vacuum, epsilon r means relative permittivity is 1. Again, as we know, epsilon is equal to epsilon naught into epsilon r. Epsilon r is equal to epsilon divided by epsilon naught. Okay. So units and dimensions of epsilon is equals to, is same as, are same as that of units and dimensions of epsilon naught. Okay. Units and dimensions of epsilon means permittivity are same as the units and dimensions of epsilon naught. So epsilon r is units less and dimensions less quantity. Epsilon r means relative permittivity has no dimensions. Again, its value depends upon nature of medium. Okay. Then for vacuum or air, epsilon r is 1. Then for vacuum or air, K is 1 divided by 4 pi epsilon naught epsilon r. But here epsilon r is 1. For vacuum, K is 1 divided by 4 pi epsilon 0, and we know value of epsilon 0. Again, 1 divided by 4 pi epsilon 0. Now we can calculate its approximate value. Nearer value will come as 9 into 10 to the power 9 units of K, Newton meter square, divided by Coulomb square. So obviously not required to write. The magnitude of 4 pi epsilon 0 is 1 divided by 9 into 10 to the power 9. Units will be reciprocal. Coulomb square divided by Newton meter square. Okay. So epsilon r, the value for vacuum is 1. Okay. And I think we have discussed for insulators. Usually, the value of epsilon r or relative permittivity is greater than 1, maybe 2, 3, 4, 5, etc. Okay. For conductor, value of epsilon r means relative permittivity is infinity. Okay. Then, in some different way, let's express epsilon r. Okay. Suppose these are two charges, Q1 and Q2, okay, separated by a distance 2 point charges Q1 and Q2 separated by a distance R. Okay. Then in air medium or in vacuum, force between these two charges in vacuum, let's take F naught, symbol, magnitude of force is equal to K 1 by 4 pi epsilon naught, because in vacuum is epsilon R 1, Q1, Q2 divided by R square. Okay. In a medium, means insulating medium, in a medium, let force between the same two charges Q1, Q2 at same distance R each 1 divided by 4 pi epsilon naught epsilon R, product of charges divided by square of distance. Okay. This is force in medium, Fm. This is force in vacuum, F naught. Then if you take ratio between force between two point charges at a given distance, force in medium divided by force in vacuum, then you may take this ratio. Q1, Q2 will get cancelled. Divided by force in vacuum, 1 divided by 4 pi epsilon naught Q1, Q2 divided by R square. See, cancels. 1 by 4 pi, 1 by 4 pi, epsilon naught are get cancelled. So what we get? Force in medium divided by force in vacuum. As we get it, all these get cancelled, means this is equal to 1 by epsilon R. So force in medium is equal to, or let's first define epsilon R, relative permittivity, in terms of forces. Relative permittivity of a medium in the space where 2 point charges are placed, that is epsilon R. Relative permittivity is defined as, it has no units, no dimensions, so only has numerical value. So relative permittivity is defined as the ratio of force between 2 point charges separated at a given distance in a medium to force between same 2 point charges separated by the same distance in vacuum. Okay, this is epsilon R. So as we observe, force in medium is 1 by epsilon R times force in vacuum. So obviously, if these are two charges kept at a fixed distance R, experiences a force F naught in vacuum and experiences a force 1 divided by epsilon R into force in vacuum, that is equal to force in medium. Thus it is observed that in the presence of medium, force decreases. How much times? 1 by epsilon R times as compared to force between 2 point charges separated by fixed distance, which is equal to F naught force in vacuum. Okay. So these are some fundamental discussions on Coulomb's law. Some another 1 or 2 points. This charge is point charge Q1. At a distance R, another point charge is Q2. Okay. If they are similar, then they repel. If they are dissimilar, then they attract. Let's consider these are two positive charges Q1 and Q2. Then Q1 repels Q2, and obviously Q2 repels Q1. Okay. Let this charge is at A, this charge is at B. Distance between them is R. Okay. So force is a vector quantity. First thing, the force between 2 point charges must start along the line joining the 2 point charges. Okay. So electrostatic force between 2 point charges, maybe this force, maybe this force. Electrostatic force between 2 point charges always acts along the line joining the 2 point charges. Okay. Let from A to B, means direction from A to B. Let's take R21, vector directed from A to B. Similarly, from B to A, direction is from B to A. If A to B is along positive x-axis, then B to A is along negative x-axis. Then from B to A, let's take R1. Then Q1 repels Q2 with a force F21 and Q2 repels Q1 with a force F1. Okay. So to take respective forces, we have to consider the proper direction of force, okay, either along R21 vector or along R12 vector. Okay. Then magnitude of force F21. K, I am taking K in place of 4 pi epsilon. I am taking K, Q1, Q2 divided by R square. But this force F21 is directed along positive x-axis, means directed along R21, means along AB. So to show direction, this is magnitude. Only just multiply an unit vector, which will not change the magnitude, but only will show the direction of force. Okay. Then in vector form, we may write K, Q1, Q2, R2 square, and direction is along positive x-axis. R21 is from A to B, means along positive x-axis. Just write an unit vector along R21. R21. From A to B, R21, which is along positive x-axis. Similarly, the force on Q1 due to Q2, let F1, we can write in similar way, Q1, Q2 by R square. Direction is along negative x-axis, F12, and direction is along BA, means from B to A, along negative x-axis. So we may take R12 cap. Okay. This is fundamental discussion up to Coulomb's law, and as we have discussed from the beginning, in lecture 4, we'll discuss all the concepts, theoretical concepts and application concepts related to Coulomb's law, and after superposition effect, we'll approach numericals, which are very interesting and enjoyable problems. I'm sure you will enjoy those questions and problems. Also, this theory is very interesting. Just you want to learn it fast, then start enjoying. You can feel this enjoyment if you do practice well. Finally, thank you, my dear students, for your nice support and encouragement. Okay. Thanks all.